All right, welcome. In this video, we're going to be looking at calculating the energy necessary for sort of particles to come into existence right at the dawn of time. And so back at the early universe's history, you would have had energy and matter that are sort of just going back and forth interchangeably. Really, it takes like a nuclear reaction to get this to go today, okay, where like we were talking about nuclear weapons or like the nuclear fusion that occurs in the sun, and it's changing, a small amount of mass multiplied by this big number, the speed of light squared, and that's like the energy that's liberated. And so at the very early part of the universe's history, there was like this interplay between energy and matter, and there's really no distinction between the two of them. They're just sort of going backwards and forwards. But as the universe expands, it gets cooler, and eventually there's just not enough ambient energy to just sort of have these particles come into existence. So whatever was sort of left at that time would have been there. And different particles, based on their mass, would require different amounts of energy. And so what we're going to calculate today is, if we have protons, we know that the mass of a proton is 1.66 by 10 to the negative 27 kilograms. And so a proton has a mass of, a proton has a mass of 0.0. Kilograms. So in standard form, we can really appreciate just how small of a number this is, right? This is why we like scientific notation in science, because no one ever wants to have to write out all those zeros every time. And they won't fit in your calculator, right? So you have to be able to sort of type it in your calculator with scientific notation. It takes both particles, okay? So like matter and antimatter collide, they annihilate, they make pure energy. That's the source of the cosmic microwave background. So these particles and antiparticles colliding, annihilating to pure energy, have been very energetic back to the dawn of time. And since then, space has been expanding, stretching those really short wavelength photons out to longer wavelength photons, right? Space is expanding, stretching the photons out, so they become longer and longer waves. So they're not gamma photons like they were, like the sun creates gamma photons at its core. They've stretched out to the microwave part of the spectrum by now. So lower energy than even the visible light that we're seeing right now, the light that's shining off of your computer screen. So we need to also consider the mass of an antiproton, and so that's like a proton but negatively charged. So it's not an electron, right? An electron is a different class of particle entirely. This is like a proton, but just negatively charged. And so it has the same mass. It's 1.66 by 10 to the negative 27 kilograms. I'm not going to write all that again. But it has opposite charge, okay? So our calculation is going to look like this. The energy, you can think about it as like the energy liberated when these two particles crash into each other that would have made some light, okay, that is still sort of raining down on the Earth today, although in the microwave part of the spectrum, or the ambient energy available in the universe when these reactions would have been sort of going backwards and forwards. When we take a look at our co-professor's sort of course here, they sort of use a schematic like, energy flying along, becomes a proton, becomes an antiproton, and heat back up again and make pure energy. And this is just kind of going backwards and forwards. So some kind of a schematic like this, if it helps you. Like I said, there's another video where I calculated this for electrons and positrons. Click on the link there if you're interested in that video. Don't forget to leave the comments down below if you beat me to the calculation. No one's yet to do it, but you might be the first one to YouTube. E equals mc squared, and we're going to have twice this mass, right? Since it's this, and like both have to be created, so we're going to double. If we're interested in a particle, it's really two of them, right? Because it's the particle and the antiparticle. So we're going to calculate the energy as twice this mass times the speed of light, which is 299,792,458 meters per second, and don't forget to square that. Physics students will hopefully remember, if you've taken physics, remember base units, kilogram meters squared per second squared. Those are the base units of joules of energy. So joule is it's like the SI unit of energy. It's a derived unit. These are all base units. And so what does that work out to be? YouTube, now's your chance. Now, some of you might have thought, oh, I already got it. I've already calculated it. I was quick, but I've had it long ago. Okay, I've had it long ago. 2.98 by 10 to the negative 10. So we say, well, that's not a lot of energy. 10 to the negative 10 joules. Well, for one, a joule is a pretty big unit of energy. James Prescott Joule, the guy that, we kind of honor him by naming the unit of energy after him, he did work with like steam engines and stuff, lots of energy. He used to look at like mechanical energy and how much heat energy was equivalent to it, sort of interesting apparatus. All right, so a joule is a pretty big unit. And one of the things that we're going to sort of fold into this calculation right now is how do we convert from joules to a more sensible unit for low energies? That unit is called the electron volt. Okay, so when energies are this small, 10 to the negative 10, we don't use joules, we'll tend to use electron volts. Without getting too much into the physics of electromagnetism, I'll just say that an electron volt is defined as the energy that an electron gains as it passes through a potential difference of 1 volt. And so, again, physics students may recognize this value, 1.6 by 10 to the negative 19 joules, as the charge on an electron in coulombs, right? So like this is elementary charge. And so as we define the energy that the electron possesses, as it passes through a potential difference of 1 volt as this energy, because that's the charge on an electron in coulombs. Okay, so it's the same value for coulombs of charge on an electron, elementary charge. It's the same charge on a proton too, it's positive, as 1 electron volt. Isaiah, you have your hand up.
I'm getting checked out. You went with this.
No, that's fine. Yeah, you guys, go where you need to go. You don't have to ask permission to sign up. You got this number divided by this number. And here's this sort of key point that I emphasized in the calculation earlier today, and I will re-emphasize to you all again right now. Your calculator rigidly follows the order of operations. Remember the order of operations? We do parentheses first, grouping symbols, then exponents, then we multiply and divide together from left to right. Then we add and subtract together from left to right. Like division is just multiplying by a reciprocal. Subtracting is just adding a negative. So they're really the same operation. It's not the rule that we multiply everything first and then divide everything next, right? We multiply and divide together. So your calculator, if you type this in like this, 2.98 by 10 to the negative 10 divided by 1.6 times 10 to the negative 19, your calculator, being the like robot that it is, following this program very rigidly, will not do what you want it to do. You want to divide by this small number. Your calculator will divide by this number and then multiply by a really small number, completely changing your answer, right? Really changing it that, because you're dividing, you're multiplying by a tiny number when you should have been dividing by a tiny number. Dividing by something small gives you a big answer, right? Multiplying by something small makes it smaller. So give your calculator the language it understands. So I'm going to take this number. Divided by, open parentheses. Got it. Use parentheses when you're dividing by something in scientific notation. 1.6 by 10 to the negative 19. And so we're getting so we got 1.86 by 10 to the 3, 6, 10 to the 9. So it's 1.86 billion electron volts, and an even sort of cleaner way to write it would be 1.86 giga electron volts. So giga, just like a gigabyte is a billion bytes of data, a giga electron volt is a billion electron volts. So giga just means 10 to the 9 or a billion. It's like this order of magnitude is the same thing as this capital letter G, it means giga, it's a metric prefix. So you need 1.86 giga electron volts, which is 2.98 by 10 to the negative 10 joules, to have protons coming into existence. What we're going to do eventually with this lesson is be able to calculate what's called the energy evolution of the universe, And we'll see how, like today, there's not this much energy available in like ambient space. There's much less energy available. But back, at the dawn of time, right after the Big Bang, there was that much energy available for these reactions to go. And so again, the idea is that at some point, space expanded enough where you didn't have them turning back into energy. They just sort of stayed. But for one reason or another, there's more of this type of matter than there is, antimatter. And the laws of physics suggest that shouldn't be the case. The laws of physics suggest there should be an equal amount of both. And so it's an open question. It's a mystery. That is the unsolved mystery with the Big Bang. Why was there more matter than antimatter way early on? Why do we live in a universe full of matter today and there's no antimatter? Let me remind everybody of the cliche. See if this will work here. The cliche sort of the whole laptop off the bench there. Come on now. This one right here. Why no antimatter? So you kind of maybe see, here's like a guy, here's like an antimatter guy. All right. So that is such a cliched example of like matter meets antimatter. Don't shake hands with your antimatter self. We're going to calculate what it would be. How much energy would be liberated if there was an anti-Dr. Flight and I shook hands with him? So I myself, and here's what you can do, guys. You can calculate the ease of me, the energy of not me, but of you. Okay? Like you are made of mass. There is a certain amount of energy locked up inside of the mass that builds you, okay, that makes you up. I happen to be 100 kilograms of mass. That's how much matter I am made up of. It used to be more than that, Awesome weight. So if I were to calculate how much energy would be liberated if I shook hands with my anti-self, then it would be 100 kilograms times, now we can round this, okay, 3 × 10⁸ meters per second, but let's be as precise as we can be just like this. So 299,792,458. My PIN number for my bank account. Oh wait, I should have pulled it up. Don't forget the square. And don't forget to double it, right? Because it's an anti, so there's also 100 kilograms of anti-Schleich out there. Hypothetically speaking, again, this is kind of, I don't know why that's always the example, but it will really happen. All right, so note that protons, much less massive than humans. Humans are made up of a bunch of these protons, right? Plus the electrons, the atoms that make us up. So we would expect a bigger number, right? 2 times 100 is 200. Why do I need my calculator for that? 299,792,458 squared equals. Now, if you wanted to calculate this for yourself, maybe you're not 100 kilograms of mass like I am, and you want to say, well, that's if you shook your anti-self. This is my journal here, and I want to know how much energy would be liberated if I shook hands with the anti-you. So if you don't know how much mass you possess, because it tends to be unfamiliar to American students, we want pounds of weight. Okay, if you know how many pounds of weight you are, weight and mass are related. They're not the same thing, right? So weight is how strongly gravity is pulling down on the mass you have, but there's an equivalence we can use, 2.2 pounds in a kilo here on Earth. On Earth, a kilo weighs 2.2 pounds. This is 1 kilogram of matter right here. Okay. I'm 100 kilos. If you take your weight in pounds, so I weigh what, like 220 pounds divided by this, that's why I'm 100 kilos, because I weigh 2 points. All right, so if you know your weight in pounds divided by 2.2, that's your mass in kilograms. And then you just plug it in here. Double it, right? So you got your anti-self accounted for. That's the very precisely known value of the speed of light. But you can round it up to 300 million if you like. And so I get 1.8, it's like 1.79 something, 1.8 by 10 to the positive 19 joules. Now that's a lot of joules. And remember, a joule is a big unit of energy. Like 1 joule is a lot of energy. And I've got 10 to the 19 joules. So if I were to shake hands with my anti-self and annihilate it to pure energy, like this was going on back in the universe's early history, a tremendous amount of energy would have been, would be liberated. And just like we did here, we're not familiar with electron volts, but it's like, it's a more sensible unit. It's better to look at like 1.86 gig electron volts than some really small, number of joules, I think. So what can we convert this to? Again, as American students, we're not as, we're at a disadvantage because we have like a different measuring system than the rest of the world. So we have to kind of we could convert it to like calories, okay? So like we think about energy of like, we get energy from food and that's measured in calories. So there's like 4.145 or something like that, joules per calorie. So we can turn to like food calories and we say, well, pizza is this many food calories. How many pizzas, would that be? Or whatever you want to do. But I'd rather calculate it in terms of atomic bombs. So an atomic bomb is about 10 to the 13 joules, which means that if I were to shake hands with my anti-self, this is a small atom bomb, not one of the big ones, but it's like, and I think this is actually the example that the co-professors use. That's why this value sticks out in my mind. You could research this on what's a big atomic bomb. But 10 to the 13 joules, and so you'd see that that's like 6 orders of magnitude greater, which means if I were to shake hands with my anti-self, it would be like 1,000,000 atomic bombs going on. And that should emphasize to you just how much energy you possess. And that's like if you converted every single kilogram of mass that you possess into pure energy. This would be energy like 1,000,000 atom bombs going on. Yeah.
So if we could make this stuff, oh my god, this many antiparticles, we could make even stronger bombs, but without the nuclear fallout.
Yeah, the only place that antimatter really exists is in laboratories here on Earth. We can create antimatter, but it's a very controlled sort of experiment because yes, it's so reactive with regular matter. And then the sci-fi sort of realm, if you watch Star Trek, it's like, oh, the antimatter containment field, that's what powers their warp drive. So they kind of, science fiction writers are kind of like, oh, this is how we would power futuristic spaceships, antimatter, matter, reactions. And dilithium crystals, I think, is enough to be up there from Star Trek. But yeah, there's a tremendous amount of energy to be harnessed in mass. So that's the promise of nuclear fusion. Okay, there are fusion reactors around planet Earth, people trying to sustain sort of fusion as a way to have fusion power plants. It's a tough reaction to make work. That's what Dr. Octopus was working on with his arm. He's trying to contain the fusion reaction like an artificial sun. And instead of achieving fusion, supervillain, that's how it goes in comic books. All right, so this would be, like I said, about 1,000,000 atom bombs. And just as a way to sort of see, you calculate it for yourself, put it into, whatever units you want to, pizzas, atom bombs, whatever. But the connection to our lesson here is that there would have been sort of these collisions occurring between all sorts of particles, like we calculated electrons earlier, protons, those are the basic building blocks of the matter we know and love. But there's a whole particle zoo, we could calculate for neutrinos and muons and neutrons, right? That's another sort of common particle. All right, and so that's the way these calculations go. Don't forget to turn that red button gray, subscribe, leave a comment down below, and we'll see you next time, YouTube.